In a recent video, we proved the existence of nth roots for positive real numbers. Now we ask, given a base greater than 1 and a positive number, can we find a real number such that the base raised to that power equals our positive number? More formally, given fixed b greater than 1 and y greater than 0, does there exist a unique real number, x, such that b raised to the x equals y? The answer is yes. We will prove that such an x exists and is unique. The proof proceeds in 7 steps, building up the necessary tools to construct and prove uniqueness of the logarithm. We'll begin by proving part A, which establishes a key inequality needed for the rest of the proof. We want to prove that for any positive integer n and base b greater than 1, a certain expression is bounded below by n times b minus 1. The key idea is to show that this expression can be written as b minus 1 times a sum. We'll discover this factorization through direct calculation. Let's start with a concrete example. When n equals 3, we want to show that a certain expression is at least 3 times b minus 1. Let's see what happens if we multiply b minus 1 by a certain sum of powers. When we distribute, we multiply b by each term, then subtract 1 times each term. Now we distribute each term, getting a sum of powers. Notice that many terms cancel out, leaving us with the desired result. Now, let's prove this factorization works for any positive integer n by multiplying it out. When we distribute b minus 1, we multiply b by each term in the sum, then subtract 1 times each term. Distributing b across the sum gives us powers from b to the n all the way down to b squared and b. Notice that most terms appear in both sums with opposite signs, so they all cancel out. After all the cancellations, we're left with the desired expression, which proves the factorization. Now, let's examine the sum that appears in our factorization. Since b is greater than 1, each power of b is also greater than 1. Therefore, each term in the sum is at least 1. The sum has exactly n terms, counting from b to the n minus 1, all the way down to b to the 0, which is 1. Since each term is at least 1 and there are n terms, the sum is at least n. Now we combine the factorization with our lower bound on the sum to complete the proof of part A. Substituting our lower bound that the sum is at least n, we get that our expression is at least b minus 1 times n. Rearranging, we obtain the desired inequality. We've successfully proven part A. The inequality holds for any positive integer n and base b greater than 1. We now move on to part B of the proof. Our goal here is to establish a similar inequality, but one that specifically applies to the nth root of our base. To do this, we don't need to start from scratch. Instead, we can build directly upon the inequality we already proved in part A. We apply a direct substitution to the entire expression. Specifically, we replace every instance of the base b with its nth root. Now, focusing on the left side, we can simplify. Raising the nth root to the nth power naturally cancels out, returning us to the original base value. This simplification leaves us with exactly the relationship we set out to prove, confirming the required lower bound for the nth root term. Thus, we have proven part B of this endeavor. We continue with part C. Our objective is to prove that for any value t greater than 1, the nth root of b is strictly less than t, provided n is sufficiently large. We begin with the result established in part B. By rearranging this inequality, dividing by n and adding 1 to both sides, we establish an explicit upper bound for the nth root of b. Now, we use the given condition on n. This specific choice guarantees that the fractional term in our upper bound is strictly less than t minus 1. Combining these results, we see that the nth root of b is less than a value which simplifies directly to t. This confirms the strict inequality and completes the proof for part C. We now prove part D. Our goal is to show that if a power of b is strictly less than y, we can increase the exponent slightly and still remain below y. We start with our hypothesis. b to the power of w is less than y. This implies that the ratio of y to b to the power of w is strictly greater than 1. We define this ratio as t. Since t is greater than 1, we can apply the result from part C. This guarantees the existence of a sufficiently large integer n such that the nth root of b is less than t. Substituting t back into our inequality and rearranging terms, we confirm that b raised to the power of w plus 1 over n is indeed strictly less than y. This completes part D. Now for part E, we want to show that if b to the w is greater than y, we can find a smaller exponent that still gives a value greater than y. We start with the hypothesis that b to the w is greater than y. This implies that the ratio b to the w over y is greater than 1. Let's define t as this ratio, b to the w over y. From part C, we know there exists an integer n, such that the nth root of b is less than t. Substituting the definition of t back into the inequality, we have that the nth root of b is less than b to the w over y. Rearranging the terms, we multiply both sides by y and divide by the nth root of b. This gives us y is less than b to the w, minus 1 over n. Thus, we have shown that if b to the w is greater than y, we can find a slightly smaller exponent such that the power is still greater than y. We are now ready to prove the existence of the logarithm. We define a set A containing all exponents w, such that b to the w is strictly less than our target value y. We will focus on the supremum of this set, which we call x. Let's formally define the set A. It consists of all real numbers w, where the power b to the w has not yet reached y. This set is non-empty and bounded above, which is crucial for our next step. Because the set of real numbers has the least upper bound property, and our set A is bounded, there must exist a least upper bound. We define x to be this supremum. This x is our candidate for the logarithm. Our goal is to prove that b raised to the power of x is exactly equal to y. First, assume for the sake of contradiction that b to the x is strictly less than y. Recall our result from part D. If we have a power less than y, we can always find a slightly larger exponent, x plus 1 over n, that remains less than y. This implies that x plus 1 over n is inside the set A. However, x was defined as the upper bound of A. Finding an element of A greater than x is a direct contradiction. Thus, b to the x cannot be less than y. Next, consider the possibility that b to the x is strictly greater than y. Using our result from part E, we know that if a power exceeds y, we can back up slightly to x minus 1 over n, and still remain greater than y. This means that x minus 1 over n is greater than every element in A, making it an upper bound. But x is supposed to be the least upper bound. Finding a smaller upper bound contradicts the definition of the supremum. We have ruled out both inequalities. The assumption that b to the x is less than y failed, and the assumption that it is greater than y also failed. Therefore, the only remaining possibility must be true. B to the x is exactly equal to y. Finally, we must prove that this value x is the unique solution to the equation b to the x equals y. Without uniqueness, we cannot properly define the logarithm. Our first method relies on the construction itself. Recall that we defined x specifically as the supremum of the set A. It is a fundamental property of the real numbers that if a set has a supremum, that supremum is unique. Since the set A is well defined and fixed, it cannot have two different least upper bounds. Therefore, x is unique by definition. For a second, more algebraic perspective, let's use a proof by contradiction. Suppose, for the sake of argument, that there are two distinct real numbers, let's call them x1 and x2, that both satisfy the equation. Since we assumed x1 and x2 are distinct, one must be smaller than the other. Now consider the behavior of the exponential function. Since our base b is strictly greater than 1, the function b to the t is strictly increasing. Therefore, b to the x1 must be strictly less than b to the x2. This is a clear contradiction. Thus, our assumption that distinct solutions exist must be false, and x1 must equal x2. We have now successfully proved the existence and uniqueness of the logarithm for any base b greater than 1.